Assalamualaikum and hi. My name is Muhammad Zikri bin Hasni from Program Product Design, number matrix 231403998. Today, I will present to you about my project simulation from course MMK 36003 Computer Aided Engineering 2. For this project, my topic is CROSSWIND aerodynamics on a cable car cabin. Without further ado, let's go for the first slides. This is the introduction and objectives of my project simulations. Computational Fluid Dynamics or CFD allows us to analyze airflow through virtual simulation. Instead of expensive physical experiments, in this project, we focus on the cable car cabins which often face dangerous crosswind in high mountainous terrains. These strong winds create instability and swaying that compromises passenger safety and structural durability. By utilizing SimFlow software, we can predict these aerodynamic forces before any physical prototype is built. Ultimately, this study helps engineers design safer cabins that remain stable even in severe weather conditions. We will go for the first objective. Simulated the external airflow field around a cable car cabin subjected to varying crosswind conditions. Second, investigated the influence of crosswind velocity on the resulting maximum air velocity and maximum pressure developed on the cabin surface. Third, analyzed the effect of cabin orientation or angle of attack on the magnitude and location of the aerodynamic loads. And lastly, the fourth objective is provided clear visualization of the flow characteristics, specifically flow separations and wake regions, to understand the stability of the cabins. Next, this is my methodology of project simulations. As you can see, this is my flowchart for this project. For the first step is geometry construction. We build a digital 3D model of the cable car and the surrounding air domain to represent the physical environment for the simulation. Next, meshing. We perform a grid independence test, or GIT, to divide the model into millions of calculation points, confirming that a fine mesh is the most efficient choice because it is 95% accurate compared to more complex settings. Then, the solver settings. We define the physics of the air, telling the computer which mathematical formulas like Bernoulli's principle to use to track how wind moves and behave around the cabin. Then we have boundary conditions. We set the specific rules for the test, such as entering the wind speeds from 10 mpsecond to 20 mpseconds and the different angles from 0, 15, and 30 degree where the wind hits the structure. Next, run the analysis. The computer processes the data, calculating the interaction between the moving air and the cabin walls to find the exact force and velocity at every point. Next, the result observation. Our findings show that doubling wind speed quadruples the pressure on the cabin, escalating from 55.7 Pascal to 222.7 Pascal, and that a 15-degree angle causes the highest local air acceleration of 12.7 meter per second. Last but not least, we also have the parametric repetition. We repeat these steps for every speed and angle combination to ensure the safety conclusions are consistent and identify the most dangerous weather conditions. As you can see, for the grid independence test, it is used to ensure the accuracy and reliability of the simulation results. A grid independence test was conducted with the primary objective of this test is to verify that the numerical solution is independent of the mesh resolutions, ensuring that further refinement of the mesh will not significantly alter the results. For this verification of grid independence test, I used three different grids. As you can see here, the first grid is the medium mesh. The second is the grid 2, which is a fine mesh. And lastly, grid 3, a coarse mesh. For selecting the best mesh densities, I use this calculation of formulas to searching for the percentage difference and choose the most minimized percentage. The table here is a data selection for grid independence test. For the first column is the mesh density, which I use the 3 different grid. Next, the division settings for each 3 grids. And next, we have a forced results from the result of the 3 grid. And next, the percentage difference, which I use to calculate the percentage difference calculation above to find the best mesh density. And lastly, the status, which is the result of the calculation from the percentage difference. From here, as you can see, I choose grid 2, which is a fine mesh for my project simulation. This is the table of results from my project simulations. As you can see, I use 2 different independent factors, which is a crosswind velocity, which use 3 different velocity from 10 meter per second, 15 meter per second, and 20 meter per second. The second factor is cabin orientation or angle of attack. I use 0 degree, 15 degree, and lastly 30 degree. And the result I choose from the maximum velocity and maximum pressure. Next, we will look to my color contour plot from the first factor, which is crosswind velocity. The picture above is my color contour plot for maximum velocity, and the below is the maximum pressure. From left, this is my first velocity, which is 10 meter per second, and the middle is a 15 meter per second, and lastly the right is 20 meter per second. Then we will look into the color contour plot for the second factor, which is the cabin orientation. As before, the top is the maximum velocity and the below is the maximum pressure. From the left, you can see this is the result of the 0 degree cable orientation. In the middle, the 15 degree, and lastly, the right 30 degree. Then we will go to the graph comparisons. This is my graph comparisons for each independent factors. From here, the comprehensive analysis confirms that crosswind velocity is the primary driver for structural loading, while orientation dictates local flow stability. A doubling of wind speed leads to a linear increase in airflow velocity, but results in a fourfold exponential surge in pressure loads. Conversely, changing the cabin angle has a negligible effect on total pressure magnitudes, but creates a critical peak in local flow acceleration at 15 degrees. These findings show that while reinforcement must focus on high-speed wind resistance, shape optimization should focus on mitigating the suction forces caused by quartering winds. Next, this is the results analysis from my project simulation. Wind speed is the primary driver of structural risk because pressure increases exponentially as wind picks up, while total pressure remains stable across different orientations. Air accelerates more sharply when hitting the cabin at a slight angle. We must prioritize overall strength for high-speed winds and optimize shape for angle stability. This is my first independent factor analysis, which is a crosswind velocity. Simulation result shows that a wind speed increases, the maximum pressure on the cabin rises dramatically following a quadratic trend. For instance, doubling the wind speed from 10 meter per second to 20 meter per second caused the pressure to quadruple from 55.724 Pascal to 222.74 Pascal. This exponential growth highlights how sensitive the structural load is to even moderate increase in storm severity. Meanwhile, the maximum airflow velocity followed a stable linear progression, reaching 23.682 meter per second at the highest test speed. This proportional scaling suggests the overall flow field remains consistent even as the magnitude of the wind is increased. Next, the analysis for the second factor, which is the cabin orientation. Simulation results indicates that rotating the cabin between 0 degree, 15 degree, and 30 degree has negligible effect on peak pressure, which remains stable at approximately 56 Pascal. This suggests that while the wind hits different parts of the structure, the maximum impact force does not significantly change with orientation. However, the maximum airflow velocity peaked at 12.718 meter per second during the 15-degree quartering wind scenario. This intermediate angle forces the air to accelerate more sharply around the leading corners compared to direct side-on winds. These findings imply that oblique wind angles may create higher local suction and potential instability even if the total pressure remains constant. From here, this is my discussions. The simulation project successfully validated on a computational model to analyze how wind impacts a cable car cabin, confirming that doubling wind speed leads to a four-fold increase in structural pressure, while the total pressure remains relatively stable regardless of cabin orientation. An orientation of 15 degrees triggers the highest local air acceleration and instability. These findings emphasize that safety design must prioritize peak storm loads rather than average conditions. Operators should be particularly alert to diagonal winds, as they create more dynamic stress than wind hitting the side directly. Future improvements could include testing rounded cabin corners and simulating sudden winds gusts to better predict real-world stability. For this study, we first made sure our computer model was accurate by testing different levels of details, eventually choosing a medium setting that balanced precision with speeds. The most critical discovery was the doubling quadrupling rule. If the wind speed goes from 10 meter per second to 20 meter per second, the pressure on the cabin doesn't just double, it jumps from 55 Pascal to over 222 Pascal. This exponential growth proves while buildings for extreme weather is the most important factor for passenger safety. We also look at how the cabin's angle affects the ride. Surprisingly, even if the total pressure stays the same, hitting the wind at a 15-degree angle causes the air to squeeze around the corners much faster, reaching speeds over 12.7 meters per second. This creates suctions and noise that could make the cabin feel shaky. Because of this, we recommend that future designs look into rounding off sharp edges to the air flow more smoothly and exploring how sudden, unpredictable gusts, rather than steady wind, impact the structure. For conclusion, this project used computational fluid dynamics to analyze how wind interacts with a cable car cabin, finding that doubling wind speed quadruples the pressure on the structure. The data revealed that while orientation doesn't change total pressure, a 15-degree angle of attack causes the highest local air acceleration and instability. These results highlight the need of structural designs based on peak storm speeds rather than the average to ensure safety. Operators should be especially cautious of diagonal winds, which create more dynamic instability than direct side winds. Future research should be focused on time-dependent gusts, simulations, and aerodynamic tweaks, like rounded corners, to reduce wind resistance. To put this into simpler terms, we use computer simulations to see exactly what happens when a cable car gets hit by high winds. The most important takeaway is that the wind forces doesn't just grow steadily. If the wind speed doubles, the pressure hitting the cable actually becomes 4 times stronger. This means we can't just build for windy days. We have to build for the worst case storm scenarios. We also found that the direction of the wind matters more than we thought. Even if the total pressure stays the same, hitting the cabin at a slight 15-degree angle causes the air to whip around the corner much faster, which can cause shaky and loud whistling noises. It turns out that diagonal winds are actually more dangerous for stability than a wind hitting the cabin directly from the side. Moving forward, We want to look at how sudden gusts of wind affect the cabin in real time and test if rounding off the sharp corners could help the air glide past more smoothly. This is my reference from the article and project simulations that I use. That's all from me. Thank you for watching.